Welcome to the Embraer E175 Systems Training Course, Electrical Module. In this module, we will introduce the electrical system, talk about the AC system and its power sources, the DC system and its power sources, and then talk about the electrical distribution system. We'll then show some typical system configurations before we talk about the system controls and system indications. Finally, we'll end with a discussion of the limitations and normal and abnormal procedures associated with the electrical system. The electrical system on the Embraer E175 is an essential source of power for most other systems in the aircraft. As such, it is designed with a high level of redundancy to ensure individual failures do not affect the safe conduct of the flight. This is especially important due to the fly-by-wire design of the flight controls, which require electrical power to operate the flight controls in flight. The fly-by-wire system can be powered by no less than 5 different power sources to ensure the flight controls are always operable. The aircraft features 2 separate but interconnected electrical systems, the AC system and the DC system. The AC system is the primary system that supplies power to most high-draw devices and also supplies power to the TRUs that supply DC power. The DC system supplies power to most individual systems, including computers, avionics, and even the passenger cabin. The AC system on the Embraer is very similar to most modern jets. It consists of a 115-volt, 400 Hz, 3-phase alternating current system. There are 5 onboard sources of AC electrical power for the AC system: 2 engine-driven integrated drive generators, or IDGs, an auxiliary power unit generator, or APU generator, a ram air turbine, or RAT, and an AC-DC static inverter. Additionally, AC electrical power can also be provided from an external ground power unit, or GPU plug, while the aircraft is parked. The Embraer features a no-break power transfer system for the AC system. During source switching on the ground, the 2 sources are momentarily connected in parallel before the first source is disconnected. This minimizes electrical transients in the system, which could cause equipment or computer errors. If the system can't parallel the sources in an appropriate time frame, which is measured in milliseconds, the first source is removed anyways, and the second source reconnected with the minimum possible break in electrical power. The integrated drive generators, or IDGs, are the primary source of electrical power for the aircraft in flight. Each IDG is mounted on and driven by its corresponding engine and is capable of providing 40 kilovolt amps, which is sufficient to power the entire electrical system from a single IDG if necessary. The IDG is really 2 machines in one casing, an electrical generator and a constant speed drive. The constant speed system is connected to the engine's accessory gearbox and receives an input rotation that is directly related to the engine speed. The constant speed system converts this variable input speed to a constant output speed, ensuring the generator always turns at the same speed, regardless of the speed of the engine. The engine turns an oil pump in the constant speed system, and this pressurized oil is routed through a series of valves into an oil motor that is used to turn the generator portion of the IDG and ensure a constant output of 400 Hz AC power. This system can be very reliable, but the work the oil does to turn the generator creates heat, so IDG oil overheats are a possibility, and therefore the IDG oil temperature must be monitored by the generator control unit, and overheats will trigger an ICAS message. Operation of all aspects of the IDG are monitored and controlled by a generator control unit, or GCU. The GCU monitors the output from the generator, and when the generator has reached operating speed, connects the generator to the electrical system via its corresponding AC bus, 1 or 2. The GCU operation is normally fully automatic, provided the corresponding knob is in the auto position. Should it be necessary to deactivate a generator, the knob can be turned to off, and the GCU will open the generator line contactor, and the generator is disconnected from the electrical system and de-excited. As mentioned, the IDG oil is critical. Should the temperature of the IDG oil exceed 335 degrees Fahrenheit, or a pressure of 140 psi, an IDG oil ICAS message will be displayed, and an amber light beside the IDG knob will illuminate. The amber light serves a critical function as it provides a direct visual confirmation beside the control knob of which IDG is malfunctioning. This is because the IDG must be disconnected once the IDG oil is overheating or overpressured. However, an IDG disconnection in flight is irreversible, so it is critical to confirm the correct IDG. The IDG can only be reconnected by maintenance action on the ground. Because the IDG disconnection is a mechanical action, the IDG knob is spring-loaded and must be held in the discon position for at least 1 second to completely disconnect the mechanism. However, to prevent further damage to the mechanism, the knob must not be held for more than 3 seconds. As a final further protection, should the IDG oil reach the even higher level of 366 degrees Fahrenheit, the IDG disconnect mechanism will automatically disconnect the IDG without pilot input. The APU generator, like the IDGs, can supply up to 40 kilovolt amps and can therefore provide all necessary electrical power for the aircraft to replace any or all IDGs without degradation to aircraft systems. Unlike the IDGs, the APU generator is directly driven by the APU, since the APU always runs at a constant speed and there is no need for an oil-driven constant speed drive system. The other normal source of AC electrical power is the external power plug, commonly referred to as the ground power unit or GPU. The GPU is connected via a plug on the lower left side of the aircraft nose. When a source is connected and the source is providing power within acceptable limits of voltage, amperage, and frequency, the avail light illuminates in the GPU switch on the electrical panel. When the GPU button is pushed in, the GPU will be connected to the aircraft network, provided that the IDGs and APU generators are not online. If any of the generators are online, the GPU will not be connected even with the button pushed in. However, should all the generators go offline, such as during a normal shutdown, while the GPU button is pressed in, the GPU will automatically be connected to the system to ensure continuous power. For the safety of the ground crew, it is imperative to ensure the GPU button is pushed out before the GPU plug is connected or disconnected. Otherwise, if other sources fail unexpectedly, the electrical system could attempt to connect the GPU while it is being plugged or unplugged, resulting in dangerous electrical discharges. Failure to do so will also prevent the electrical system from detecting a subsequent GPU connection until the button has been cycled off to reset the GPU quality detection system. The ground power can also supply a ground service bus, which only powers cabin lighting and electrical outlets in the cabin. This bus is intended for use by maintenance or groomers to allow aircraft servicing when the aircraft is otherwise powered off. The GPU, if connected, can be connected to the ground service bus via a switch on the forward flight attendant panel or the panel next to the GPU plug on the aircraft nose. The static inverter is a very small device that converts DC power to AC power. The static inverter, when needed, uses DC power from the aircraft batteries to provide a very small amount of AC power to the aircraft. The static inverter is limited to 250 volt amps, less than 1% of the power rating of any of the generators. It is intended to provide limited AC power to essential systems until the RAT comes online. The RAM Air Turbine, or RAT, is the final emergency backup source of AC electrical power for the Embraer. The RAT is a windmill that deploys when all other AC sources, except the inverter, have failed, to provide a final source of AC electrical power to essential systems, especially the fly-by-wire system. When all 3 AC generators are offline during flight, the RAT door opens automatically and the RAT falls into the slipstream, where airflow turns the windmill and the attached generator. There is also a handle in the flight deck to deploy the RAT manually should it not deploy automatically when needed. 8 seconds after the RAT falls, the generator is connected to the electrical system. The generator provides the same 115 volts and 400 Hz, but only 15 kilovolt amps. The RAT will not power all systems, but will ensure essential systems remain operable. The 8-second pause during deployment allows the windmill to reach full speed without resistance from the generator. It is during this 8-second period that the static inverter supplies power to essential systems. The RAT, once deployed, cannot be retracted and will remain deployed until maintenance action after the flight. It should also be noted that the rat is very noisy due to the high rotation speed needed to generate the 400 Hz AC. To ensure sufficient airflow over the windmill, the airplane must remain above 130 knots indicated airspeed until after landing. If the speed falls below 130 knots, the system will begin to shed additional loads to ensure the rat does not stall prematurely. First, the rat will shed the standby AC bus, and the inverter will resume using the battery power to supply the standby AC bus. In this case, the rat is only powering the AC essential bus. Should speed decrease further, the rat will eventually stall and cease supplying power to the AC essential bus as well. It should be noted that the rat, through the AC essential bus, will power the AC motive pump 3 alpha for the hydraulic system, thus providing limited hydraulic power for flight controls, even in case of a dual engine failure. The DC system on the Embraer is a 28-volt system supplying power to most of the electronics and computers located throughout the aircraft. There are 5 sources of DC power on the aircraft, 3 TRUs and 2 batteries. Additionally, an external DC power source can be connected to the aircraft through a plug near the tail. However, this external source will only provide DC power to the APU start bus and no other systems. The transformer rectifier units, or TRUs, are the normal source of DC power on board the aircraft. The TRUs convert 115-volt AC power to 28-volt DC power. The 3 TRUs are labeled number 1, number 2, and essential, and all are identical but are connected to different circuits. Each is capable of supplying up to 300 amps to their respective DC bus and other connected buses. TRU1, as you can see here, supplies DC bus 1, DC essential bus 1, the DC ground service bus, and the hot battery bus 1, and also charges battery number 1. TRU2 provides power to DC bus 2, DC essential bus 2, hot battery bus 2, and charges battery number 2. TRU essential supplies power to DC essential bus 3. A pair of 22.8 volt, 27 amp hour NiCad batteries serve as a backup to the TRUs and provide DC electrical power prior to other sources being connected to allow an APU start or during rat deployment. The batteries are recharged during operations by an available source of DC power and can even be charged by the rat through the essential TRU. In an electrical emergency with no AC generators online, if the rat fails or stalls, the batteries can supply electrical power to essential systems for up to 10 minutes. If the aircraft is left on battery power alone while on the ground for more than 5 minutes, a horn will sound outside the aircraft to alert ground personnel that the batteries may be discharging. Care must be taken to never leave the aircraft unattended for extended periods of time with the batteries left on. Should other power sources such as the ground power unit fail while the batteries are still on and the batteries fully discharge, then extensive maintenance operations are required. The batteries, even when off, provide a very small electrical current through the hot battery bus to numerous systems, including flight control rigging computers. Should power fail completely to these computers, many critical memory settings are lost, requiring not only battery replacement, but extensive re-rigging of all the flight control systems and computers, and potentially days of aircraft downtime. The electrical distribution system of the Embraer routes power to various systems through a series of electrical buses. The system is designed to ensure a high level of redundancy so that single failures cause little disturbance to aircraft systems. The system is also highly automated, requiring minimal crew input for normal operations. Electrical power distribution is handled by 4 Integrated Control Centers, or ICCs, and 2 Secondary Power Distribution Assemblies, or SPDAs. The 4 ICCs, Left ICC, Right ICC, Essential ICC, and Auxiliary ICC, route power to the various electrical buses while monitoring for faults. Each ICC incorporates thermal circuit breakers, line replaceable units, or LRUs, line replaceable modules, or LRMs, and the various AC and DC buses. The design of these ICCs, and especially the LRUs and LRMs, allows for quick replacement of worn or broken components to ensure the aircraft can be quickly returned to service. each ICC contains specific buses as indicated in the list on the screen. SPDAs are load management units which route power from the ICCs to the buses contained within each SPDA. SPDA 1 is located in the forward avionics bay, and SPDA 2 is located in the mid avionics bay. Each SPDA consists of a number of slots where various electrical modules can be plugged in, providing functions such as communication, data processing, and power distribution. Each of the two SPDAs distributes power on behalf of a number of buses, and each SPDA itself is powered by 4 different buses as listed here, ensuring that both SPDAs remain powered in almost any electrical power failure scenario. Each SPDA also uses an AirInc 429 bus to communicate with the ICCs and the MCDUs in the flight deck, allowing crew to directly monitor and interact with the SPDAs. One of the most important tools in connecting the various parts of the electrical system are the bus tie contactors. These electrical relays connect various buses to another bus, or an output bus, or a component. These are how the electrical system reconfigures itself to maintain power to as many buses as possible. Each power source has a contactor that connects it to the network if the source is healthy and in use. Contactors also link different buses together. However, many contactors are normally open, allowing the aircraft to run with essentially 3 parallel electrical networks. If a source fails, then the networks may be linked together to share a common power source. However, this parallel architecture helps ensure that any faults within a single part of the network do not cause other networks or parts of the electrical system to fail. Some of the bus tie contactors can be controlled by the pilot through switches on the overhead panel, but many are only controlled automatically and cannot be manually opened or closed by the pilot. The biggest advantage of the SPDA architecture is the solid-state power controller, better known as an electronic circuit breaker. Instead of a large panel of manual thermal circuit breakers in the flight deck, most systems on the Embraer are controlled by electronic circuit breakers in the avionics bay. These circuit breakers will trigger a message on ICAS when tripped and can be reset via the MCDU. The breakers can also be manually tripped or reset when requested by a checklist or by maintenance through the MCDU. Not only is it easier to monitor and control a large number of circuits without even getting up from the pilot seat, but finding the needed breakers is much easier as the circuit breaker menus in the MCDU are sorted by system. The system is accessed by using the CB button on the MCDU. This button brings the pilot to the CB menu. The main CB menu allows a pilot to see a list of out or lock circuit breakers, a list of all the circuit breakers listed by system, a list of all the circuit breakers listed by the attached bus, and a list of all the tripped fuses. Note that the fuses are non-resettable and their status is provided for information only. Additionally, pilots are alerted to a tripped circuit breaker by the message CB tripped appearing on ICAS. The actual CB that is tripped can be viewed on the Out Lock page on the MCDU CB menu, and when the line select key beside this new tripped circuit breaker is pressed, it acknowledges the tripped circuit breaker, and the CB tripped message is cleared from ICAS. It should be mentioned that, like traditional circuit breakers, tripped remote circuit breakers should not normally be reset in flight unless required by a checklist or if the pilot in command considers it necessary for the safe continuation of the flight. Remote circuit breakers, like their normal thermal cousins, are designed to stop circuits from overloading. Resetting a tripped circuit breaker without determining the cause could lead to an electrical fire and should only be done after careful consideration. In addition to the remote circuit breakers within the SPDAs, there are a number of traditional thermal circuit breakers. On either side of the flight deck, near the floor beside each pilot, is a circuit breaker panel containing a number of the more critical circuit breakers, including breakers that feed into some of the critical buses. These circuit breakers can be reset by the pilots in a traditional manner in accordance with the company's circuit breaker reset policy. There are a few more thermal circuit breakers in the aircraft located in the avionics bay as well. These circuit breakers are inaccessible in flight and must be reset by maintenance only on the ground. As mentioned before, all electrical power is distributed around the aircraft by a series of buses. A bus is an electrical connector that provides power from a source to many different systems, while tie contactors are the relays that connect the various buses together to maintain power to all buses from the available sources. Different buses allow circuits to be grouped by priority to ensure redundancy across the system and also to ensure that the most important items are most likely to retain power. The bus system consists of AC and DC buses which serve different purposes as indicated by their names. For example, AC Bus 1 and AC Bus 2 are the primary buses that feed AC power to most systems, usually from IDG1 and IDG2 respectively. Normally, buses 1 and 2 are not directly linked so that a problem with one source or a fault in one bus does not affect the other bus. However, each bus can be fed by other sources according to a power hierarchy, depending upon the available sources. The priority of power sources for the main AC buses is as follows. The same side IDG, such as IDG1 feeding AC Bus 1. If an IDG is offline due to a failure or even an engine shutdown, the next choice is the APU generator. If the APU generator is unavailable, the GPU will be used if available, and the button is pushed in. If neither the APU or GPU are available, then the offside IDG, if operating, will be the power source. This priority serves well for both normal and abnormal operations in flight and on the ground. There is also an essential AC bus. This bus contains a small set of essential equipment that will keep the airplane flying even if AC buses 1 and 2 are both failed. The equipment on the AC essential bus includes hydraulic pump 3A, fuel pump 2A, a slat channel, a flap channel, and the essential TRU. The priority of sources for the AC Essential Bus is normally AC Bus 2, but will automatically switch to AC Bus 1 if AC Bus 2 fails. If both AC buses have no AC power, then the RAT will auto-deploy and provide power to the AC Essential Bus only. While the RAT is spooling up to operating power, the AC Essential Bus is unpowered, but the AC Standby Bus, which is normally fed off the AC Essential Bus, receives power from battery 1 through the DC-AC inverter. This keeps a very small number of AC systems running until the RAT is online. The DC systems are normally powered by the TRUs in flight. TRs 1 and 2 power the main DC buses and the 1 and 2 essential buses respectively. DC Essential Bus 3 is powered by the essential TRU. If there is no AC power available and thus no TRUs are powered, the batteries power only the essential DC buses. The main DC buses will only get their power from TRUs. As you can see, the flow of power on board the aircraft in this diagram is normally top to bottom. Normally, the sides of the aircraft are kept isolated to avoid faults affecting multiple buses, but should a normal power source fail for any bus, the system will automatically reconfigure to take power from an adjacent bus. For example, a failure of IDG2 will result in the system connecting AC Bus 2 and 1, and all AC power will be obtained from IDG1 through the AC Bus 1. If the APU is started after this failure, the APU will then power AC Bus 2, and AC Bus 1 and 2 will be isolated again. The DC buses operate in the same fashion. While normally isolated, if TRU2 were to fail, the system would connect DC Bus 1 and 2 together to power all of DC Bus 2 systems from TRU1. Note that then to balance this load, the system will disconnect DC Bus 2 and DC Essential Bus 2 and switch to powering the DC Essential Bus 2 from the DC Essential Bus 3, thus sharing some of the load with the essential TRU. In almost all cases, a single point failure in the electrical system will result in reconfiguration without any crew action or lost systems. Control of the electrical system is handled from a single panel on the left side of the overhead panel. The panel is laid out more or less diagrammatically with the AC system at the top and the DC system at the bottom. The electrical system is mostly automated, so like most other panels, the switches will remain in the 12 o'clock or up position until a failure occurs. Each IDG is controlled by a 3-position switch. Normally the switch is in the auto position and the generator is automatically connected to the system once it has reached operating speed without any pilot action. An off position allows the pilot to turn off the IDG manually in case of malfunction or to allow a reset by turning the generator off and on again. The third position is the disconnect position. This position is spring-loaded back to off and must be held for 1 to 3 seconds to disconnect the IDG's drive mechanism. Remember that this action is irreversible in flight, so confirm the correct IDG is disconnected. Incidents have occurred in the past where the operating IDG was disconnected instead of the faulty one, resulting in a total loss of electrical generation during flight and an electrical emergency configuration. To aid identifying a faulty generator, an amber LED is located directly adjacent to each IDG switch. This LED illuminates for the corresponding IDG when the IDG oil message appears on ICAS, aiding in identifying the correct switch to disconnect a faulty generator. Below the IDGs are a few more switches. On the left is the GPU switch light. This is one of the only switches on the electrical panel that is operated regularly. Pushed out, the GPU is inactive. When pushed in and the avail light is on, the GPU becomes available, though it will only be connected if there is not a higher priority electrical source connected. The switch light contains two lights. Avail indicates that the GPU is connected and is outputting appropriate voltage, amperage, and frequency, but it is not connected to the electrical system, either because the switch is out or a higher priority power source is connected. More about source priority in the next section. If the GPU is connected to the system, the avail light goes out and the in-use light goes on. It is imperative that, even if the in-use light is not illuminated, the GPU switch is pushed out prior to instructing ground crew to disconnect the GPU. This ensures the GPU monitor is reset for the next connection. This also prevents dangerous, possibly fatal discharges as the plug is removed should the GPU monitor reconnect the GPU to the system as it is being removed. It should be noted that these two lights on the GPU switch are replicated on the GPU plug panel on the nose of the aircraft, so ground personnel can also see if AC power has been recognized and or is being used. However, ground crews should never disconnect ground power based solely on this indication, but should be in communication with personnel in the flight deck to ensure the correct position of the GPU switch. There is also an APU Gen switch. This is very similar to the IDG switches. It is normally auto and connects the APU to the AC bus ties when the APU generator is outputting appropriate AC power and there is no higher priority source connected to the AC buses. The switch can be pushed out to turn off the APU generator and prevent it from connecting to the electrical system, or to attempt a reset. When the button is out or off, the white light in the switch illuminates. Between these two switches is a controller for the AC bus ties. This switch is normally in the center, auto position, where it opens and closes the bus tie contactors between AC bus 1 and AC bus 2 according to system logic. If the switch is turned to the 1 open position, bus tie contactor 1 is opened, which isolates AC bus 1 from AC bus 2 as well as the APU generator and GPU plug. 2 open will similarly isolate AC bus 2 from the other AC bus as well as the other power sources. Next on the electrical panel are the TRU control switches. Again, in the auto position, these are controlled automatically by the electrical system and will come online as soon as their source AC bus is providing power. The off position allows each TRU to be disconnected from the output DC bus in case of TRU malfunction or to help isolate system faults. Once again, for the DC system, there is a bus tie contact switch. This switch has two positions. In auto, as you may guess, the system functions automatically to open and close the bus tie contactors to maintain power to each DC bus normally from its respective TRU. Selecting the switch to open will open all the DC bus ties, isolating the 1, 2, and 3 DC buses from each other and ensuring no faults can propagate to other buses. The final switches on the panel are the battery switches, which are slightly different for each battery. Both batteries have an off position which disconnects the hot battery bus from the DC essential bus, essentially depowering the entire airplane. Battery 2 has an auto position where the hot battery bus 2 is connected and disconnected from the essential bus automatically. It is normally connected at all times in the auto position, except during battery APU start. During the APU start, the hot battery bus is isolated from the DC essential bus, so the battery provides max power to the APU start bus to start the APU. Once the start is complete, the hot battery bus 2 is reconnected to the essential buses. On the other hand, battery 1 is never isolated from the DC essential buses. and continues to provide power to the essential buses even during the APU start, ensuring a constant voltage is maintained throughout the APU start. Hence, its switch is simply on or off. There is one additional control for the aircraft electrical system, the RAT manual deploy lever. This lever is located on the pedestal under a guard. Lifting the guard and pulling the lever will deploy the RAT in case it is not automatically deployed when needed. Regardless of whether it is deployed manually or automatically, the RAT will remain out for the remainder of the flight and can only be stowed by maintenance on the ground. The status of the electrical system is mainly observed through the electrical synoptic page on the MFD. This page shows a diagram of the major components of the electrical system, not unlike the diagram shown previously. The diagram uses a color scheme much like all other synoptic pages. Any component or line shown in green is operating normally. White indicates a component that is off. Amber indicates a component that has failed or operates abnormally, and amber dashes indicate a component whose status is unknown. Even the lines connecting the various buses will turn green when voltage is detected in the corresponding connection, or white if no voltage is detected. All of the major components, aside from the buses themselves, also have digital readouts on the page indicating important parameters such as voltage and amperage, AC component frequency, and battery temperature. As with the components themselves, green indicates valid values, while a pair of amber dashes instead of a number indicates that no valid data has been received. It is important to note that some of the components that are normally used in flight are removed from this diagram when they are not in use to declutter the display. This includes the GPUs, the APU Gen, and the RAT. There is one other page where electrical systems information is available. On the MFD status page, the battery voltage can be seen. This allows crews to confirm the battery voltage during power-up prior to connecting an AC source. Once an AC source is connected, the voltage seen on the display is the voltage that is charging the batteries. There are very few limitations associated with the electrical system in this aircraft. However, it is always prudent for crews to monitor the output of the various electrical systems and ensure that they are operating within the prescribed limits. One of the limitations of the electrical system is that, for an APU start, battery 2 must be at or above minus 20 degrees Celsius in order to ensure it has sufficient power to start the APU. One other important limitation is that prior to departure, the battery voltage must be above 22 volts. If, upon power-up, the batteries are not at 22 volts, they must be recharged per the table indicated here. Failure to charge the batteries properly prior to departure may result in batteries that do not have a sufficient reserve of charge to power the aircraft through an electrical emergency. Now let's look at using the electrical system in a typical flight. As always, follow your appropriate checklists and SOPs. At the start of the day, the crew walks onto an unpowered airplane. The first step is to turn on batteries 1 and 2. This powers up the basic electrical system and allows the power system relays to start working. If the GPU is available, it can be connected now. If not, then the APU can be started. Don't delay connecting an AC power source. The batteries are not intended to power the airplane for an extended period of time and can discharge to the point where starting the APU is not even possible. Once the GPU or APU generators are online, all electrical systems are powered. If it is not already started, the APU is usually started 10 minutes before departure. Once it is available, allow the power to stabilize for at least 10 seconds, then deselect the GPU and instruct the ground crew to remove it. During engine start, the IDGs come online automatically and take over supplying their respective bus from the APU. After engine start, the APU is normally shut down and the airplane is run off the IDGs alone. After the flight, approaching the gate, the APU is restarted. Once the APU has been stabilized for at least 10 seconds, the engines are switched off and the APU generator automatically takes over as the IDGs fall offline. Once the GPU is connected, the APU can be shut down. As the APU shuts down, the GPU is connected to the system. Prior to leaving the airplane, the crew disconnects the GPU and then turns off the batteries. Unlike many aircraft, the GPU should not be left powered with the batteries off. The highly computerized nature of the Embraer means it does not respond well to being powered up incorrectly, as certain computers expect other computers to respond at a certain time. If an aircraft is encountered with the GPU connected and the batteries off, the recommendation is to disconnect the GPU and restart the aircraft from a cold and dark state to prevent potentially spurious faults from appearing later during flight. We will now review the applicable checklists for various electrical failure scenarios. As always, follow your checklists when performing any procedure. Some of the ICAS advisories related to the electrical system are pretty benign. Load shed, remote CB trip, rat fail, and inverter fail have no associated procedure, though it would be prudent for the pilots to analyze what circuit breakers have tripped on the MCDU after a remote CB trip message and determine the ramifications. The SPDA failure checklist simply informs pilots that, depending on exactly how the SPDA has failed, thrust reverse may not be available after landing. The GPU connected ICAS message only appears if the parking brake is released while the GPU is still powering the aircraft. Ensure the GPU is disconnected prior to taxi. If the IDGs, TRUs, or APU Gen are off, almost all the checklists call for the failed component to be turned off and on again. If this reset is unsuccessful, then the failed component should be turned back off. In the case of an IDG failure, starting the APU should be considered to bring a new power source online. Also, note that the essential TRU should not be reset off and on, but simply turned off. IDG oil messages indicate that an IDG is experiencing high oil pressure or temperature within the constant speed drive. The only remedy is to disconnect the IDG. Be sure to confirm the correct IDG with the illuminated panel LED to avoid disconnecting the wrong IDG, as this step is irreversible in flight. If either battery off message appears, be sure to select the battery back to auto or on, unless the battery was turned off for a particular reason. If battery 1 is off, then the APU cannot be started. If the BAT 1 or 2 discharging messages appear in flight, the associated TRU should be turned off and on to attempt to re-establish power to DC buses from the proper TRU. Note that BAT 1-2 discharging may appear on the ground when the batteries are turned on, but an AC power source is not available. This message takes about 30 seconds to appear, so it is not normally an issue when connecting the GPU right away, but may be an issue if the APU is being started because no GPU is available. In this case, allow the APU to finish the start, and the message should be removed. If any of the buses go offline during flight, the appropriate bus off ICAS message will appear. The checklist for each bus is unique and will alert the crews to further steps to take to isolate the bus and protect the remaining systems, as well as alerting the crew as to what systems will become unavailable. Any single bus failure may reduce aircraft functionality, but should allow sufficient remaining systems to safely complete a flight. The main AC buses primarily result in electric hydraulic pump and ice protection degradation, as well as the loss of some fuel pumps. The main DC buses will result in loss of auto throttle and numerous other systems, which are listed in the checklist itself. This allows the crews to evaluate the aircraft and make a plan based on the remaining systems. Loss of the DC essential buses will call for disconnecting the battery to prevent battery discharge, and a loss of some ice protection. Numerous other systems are lost. Again, the checklist provides a full list of all lost systems. Several warnings are associated with the batteries. If a battery overheats, it should be turned off immediately to stop charging and hopefully stop the overheat condition. If both batteries are off, the aircraft should divert immediately and the APU cannot be started. If the BAT discharging warning appears during flight, again, an immediate diversion is required. The final and most complex abnormal involving the electrical system is the electrical emergency, which indicates that all AC generators have gone offline. Due to the fly-by-wire system used on this aircraft, maintaining electrical power is critical to continued operation, so the total loss of all electrical power is a long and complex emergency. The electrical emergency is often shocking when it occurs, as many key systems fail simultaneously, including many of the screens, the autopilot, the autothrottle, and many other systems. Following the checklist attempts to restore electrical power by resetting the IDGs and starting the APU. If none of this is successful, then the rat must be deployed. While it should have deployed automatically, the manual release can be used if the automatic deployment did not work, as so indicated by the battery's discharging ICAS message. Once the rat is available, a minimal amount of systems are restored to allow continued flight. However, the crew should carefully read the list of failed systems and consider their implications. Among the lost systems are 3 of the 5 screens, the autopilot, auto-thrust, flight directors, reversers, all spoilers, anti-icing systems, most electric hydraulic pumps, and much more. This is a critical emergency, and a landing should be considered at the closest suitable airport, as any further failure could potentially render the airplane unflyable. We will now answer some review questions regarding the material covered in this presentation. Try to answer the question before the answer is displayed. Pause the video if necessary to give you the time to answer the question. Let's begin.